Now this has improved the performance of our Focus Fusion 1 or FF1 device over all the other plasma focus devices that have been operating over the past 40 years. This is a graph that shows neutron yield, again plotted logarithmically, against the peak current in kiloamps. And basically all these dots down here are other fusion experiments with the same type of device, with the same dense plasma focus. This is our curve here of our results. And basically what you see is that our results are almost an order of magnitude bigger in yield for the same current and are on a very steep rising slope. Now this is the device that we've built over the past year. Actually, it started functioning almost exactly a year ago, October 15th. We started building it basically in March of last year, March of 2009, completed in October 15th. Now what you see here is the capacitors that store the energy that when the device is fired, in a few millionths of a second, feed the energy into the central electrodes. And these electrodes are shown here without the vacuum chamber that surrounds them. When it's operating within a vacuum chamber. And this is a close-up of the core of the device, which are two copper electrodes that the current flows between to form the plasma focus. So this is the inner electrode, or the anode, and these are the outer electrodes called the cathode. And this whole thing, this inner electrode is only a couple of inches wide. And this is another view of the 14 centimeter long electrodes, which are the ones we're currently using. Now, in this first year, we've had a number of achievements. One is that we've had clear and repeatable confirmation that we can achieve high ion and electron energies, more than 60 keV. That's over half the ion energy needed to ignite PV11. 9 years ago, at other experiments in Texas A&M University, we first achieved these very high temperatures. But it was only in a small number of shots, and we needed to confirm this. Now, repeatedly, in a large number of shots, we've been able to confirm that. We've achieved more than a 15-fold increase in the maximum energy efficiency. And I'll have more to say about that in a minute, which is the fusion yield per unit input of energy to a capacitor bank over the Texas A&M experiments that were done a decade ago. Since our first shots with Focus Fusion 1, we've achieved a 10,000-fold increase in yield. Now we're exceeding by at least twice the energy efficiency for a given total bank energy that trend line of all other DPF experiments. That is, there have been experiments that have achieved better energy efficiency, but only with a much bigger total bank energy. And we're exceeding by at least fourfold the trend line of fusion yield versus current. That's what was illustrated in the graph I just showed you. And we've achieved a partial confirmation, which I'll also explain in a minute, of the efficacy of the axial field coil in increasing fusion yield. Now, I want to talk about some of our results. One of our results is we have gotten excellent photographs, thanks especially to Fred's help, with the ICCD camera. And the ICCD camera is a electronic camera like those that we use every day, except for exposure time. Its exposure time is as low as 1/5 billionth of a second. That makes it a lot faster than our everyday cameras and a lot more expensive. Now, this is a picture showing in our own device one of the stages that you just saw in the animation, which is the stage where all of the filaments are fountaining together in the center of the anode. This glowing disk here is the plasma glowing inside the hole in the anode. And this is at a point where the filaments have reduced themselves only to about 4 or 6 filaments. You can see the filaments, coming in from the sides and going into this focus region. And then we were fortunate enough that the plasmoid itself only exists for about 10 nanoseconds, so it's hard to catch it timing exactly. But we were fortunate to catch it. And this is an enlargement of an actual plasmoid. And you can sort of faintly see the twisted filament that surrounds the plasmoid. This bright area is the plasmoid. These little spots, those are not real. Those are individual pixels of the camera. So it's not that you have to imagine that this is all smoothed out. The resolution of the camera is about 60 microns. So we can just barely resolve the 150 micron wide plasmoid. Now it's very important to get these images basically to see what size the plasmoid is, which also gives us a cross-check on the density of the plasmoid. So where are we? Well, again, I'll go into this a little greater depth, but we're a bit less than halfway there. We've been slowed down by problems with the switches. We've been working for about 6 months to get the switches to all fire together. We managed to move up from 25 kilovolts to firing at 35 kilovolts on our way to 45 kilovolts. We also have to test other electrodes and move on to BB11. Right now we're operating with deuterium. Let me stop here. We'll go back to some of the data, and I want to show you how the machine actually works in practice. And this will be our first surprise. This is a video of a shot that was taken just yesterday. And this will show the machine in action.
25. Okay, so right now the pumps are pumping down the chamber. Chamber is evacuated, and I am closing these valves. These valves shut off the valves to the roughing pump and the turbomolecular pump. So I can pressurize the chamber at this point. The next thing I'm doing is I'm increasing the pressure in the regulator. That's the gas that I'm going to use for filling up the chamber. And I'm beginning to fill. While Eric is going inside, I think, to... Yeah, go ahead.
I turn on the trigger.
Turn on the trigger. Let's see what this means.
I check our little coil. It's down up a little bit. Turn on the trigger.
That was it? Something over there?
Yeah.
All right.
And then...
There? Turn on the big guy?
And we turn on the high voltage distribution.
Oops.
Get the heck out. As I'm filling the switch with with a particular pressure. Right now for this experiment it's 13.5 psi. The trigger is at 9 psi. The pressure inside the trigger generator. Okay, that should do it. A little bit. Okay, that will still work. And then the next thing is I'm filling the chamber. That's usually the last thing I do to prevent the impurities from filling in. Alright.
Just wondering why the fan
always overshoots a little. But I think I can do it. There. That's 30 torr.
Okay. I think we're ready.
Okay, this is 12.5 and 13.5, 9.1 and 30 torr. Are you on, Derek?
Yeah.
Okay, everything's on, everything's ready to go. So then I remove the dump so that the capacitors can now get charged. Then the power supply is turned on and I begin charging now. Charging to 33, 5, 10, 15, 20, 25, 30, fire, 33.6, fire, 1, 2,
Another picture of the little extra.
3, So I turn off the trigger each time because the life of the cables when exposed to high voltage depends on how long they are exposed to it. So we try to minimize them. And comes 5. 5 is when I start pumping the chamber down. So you can see the pressure is dropping now. And 6 is essentially I turn off the
Well, that's kind of
optical converters. And then I start acquiring data on the computer.
Shot number 2.
All right. First, let's see how many fired. All right. Here's the suspense. 1 fired. 2 fired.
We got some neutrons already.
Okay. All right. 4 fired.
So all those bubbles were a
11.
nucleation site
5 fired.
caused by a neutron.
You're gonna have to hold that against the
7 fired.
dark background.
9 fired. 10 fired. 12 fired. All 8
fired.
They
fired.
fired!
Way to go.
High five.
All
High five,
right.
high five, high five. Finally,
All right.
after so much struggle.
So now we have to do it. We have to,
Yeah, we have to repeat it.
We have to repeat it.
Yeah, we have to
Repeatability.
$33.4
Oh.
fire.
This is a very different picture.
2.
Okay. Go up, go up, go up.
This picture has a very bright spot in it.
Right. Let's see whether we did it again. 6. Yes! Now, yes, yes, yes,
Consistent. Now, okay.
yes, yes.
Finally.
We'll get what Reswan calls hours of fun out of analyzing this shot, I'm sure. All right, so that was surprise number 1, which is after all these months, we now actually do have reliable firing of all the capacitors together, and we've shown this since yesterday in 6 consecutive shots firing all the capacitors together. At the moment, we are firing 8 capacitors, not 12, because of previous breakages